Please take your seats. We are about to resume. And I introduce Emily Cutting, who is actually, we have worked together all these last 8 months very closely, spinning around emails, even late at evening hours, for make this event possible. So I thank you personally for all what we have done together and your organization at ATAXIA UK for this event. And thank you, Emily, and I'll let you chair the next session.
Thank you, Vasilis, and to everyone else that's been involved in the organisation. You're all probably sick of emails from me, but, you know, I'll leave you alone now, probably. So I'm honoured to be chairing this session, which is a session where we'll be joined by junior ATAXIA researchers, and it's their opportunity to engage with this community. As you'll see, everyone is joining us remotely, so hopefully they're all there waiting on Zoom, ready to join us. Do we know if Holm is online? Okay, so there will hopefully be a small change to the programme, and Holm Gressner will hopefully join us as well for this session. But for now, I'm not sure he's online yet, so for now we'll start with the flash talks. So first we have Rosella Abetti joining us from University College London, and she's going to talk about Bench to Bed, a story of a novel compound.
So thank you, Emily, for the introduction. Yes, I'm a senior research fellow at the ATAXIA Centre, London, at the Institute of Neurology, UCL. I first of all would like to thank the organizers of this meeting to give me the opportunity to overview my work today. And it's a real pleasure to be with you, although remotely. My story today is a successful story of a promising compound and how it goes from the laboratory to the few years ago, Reata Pharmaceuticals approached us and asking to investigate the efficacy as an antioxidant and an anti-inflammatory compound to try on our models of Friedreich ataxia. As you know, inflammation and oxidative stress are key features of this disease, and so it was logical as well to try and say, yes, let's do it. So we first isolated neuronal cells from cerebellum from 2 mouse models. Then we also isolated fibroblasts from skin biopsies from our cohort of patients at the ATAXIA Centre, in which I lead the mitochondrial basic research. And then we used sophisticated techniques such as confocal microscopy to identify reactive oxygen species inside the cells and to evaluate the bioenergetic of the mitochondria, which mitochondria are the powerhouse of the cells here and are very important for cell viability, amongst the other things that already Helen Puccio showed and mentioned. So while measuring the mitochondrial function, we've also managed to assess that one of the complexes of the driving force that lead to produce energy was inhibited, and the substrate for this complexes also was lacking. On the other side, we know that in Friedreich ataxia, there is a suppression of the antioxidant pathway, which is, let's keep it simple and name it just NRF2 pathway. And it's the endogenous antioxidant pathway that helps to protect the cells from oxidative stress. So in Friedreich ataxia, this main player is usually degraded under oxidative stress. Therefore, the cells cannot defend themselves. by administering omaveloxolone, we managed to release the activation of NRF2. And NRF2 is known to trigger the expression of protein, the antioxidant proteins, and therefore counteract reactive oxygen species in the cells. So during our experiment, we saw that omaveloxolone not only was suppressing the oxidative stress, but also was ameliorating the mitochondrial function, so counteracting mitochondrial dysfunction, directly through the complex one that we found that was inhibited. So this study was amongst several other studies around the world about this compound. It was crucial for paving the way towards clinical trials, and then clinical trials were successful and led to just at the end of February, led to this compound to become FDA approved. So this is now the first drug that is FDA approved as a cure for Friedreich ataxia. And so we were absolutely thrilled that how everything went from our experiment in the lab up to our patients that are very dear to us. And yes, and my paper is here. I don't know if you can see, because this seems the screen here is on the slide.
I'm not sure the slide, Rosella, sorry to just interrupt you. I'm not sure the slides are moving on. Have you moved on past the first slide, Rosella?
No.
No. Okay, sorry. Carry on.
It's one line. Yeah, no, it's just, can you see, do you see my face on it? Because I was hoping not. I mean,
no, we see
the face, the gallery sort of hide my, sorry, my slide.
We see your slides. We see the first slide still with the title and the first images. Yeah, okay, good,
yes.
Thanks. Great, carry on.
Picture
Sorry.
one slide to summarize everything.
Thank you.
So, and with this, I would like to thank, first of all, the patients that help us with the study, and also all the founders that help us developing the studies, and of course my collaborator who helped me develop the story, and you for listening to me. Thank you.
Thank you. I think as with the other sessions, we'll go through the presentations and then we'll have time for questions at the end. So thank you very much, Rosella, for your presentation. So next we have Ana Claro coming from IS3 in Portugal. You can see her, I think she's there. I think you can share your screen, Anna, when you're ready. Anna's going to talk about nanobodies to combat Mercado-Joseph disease.
Okay, thank you everybody. My name is Ana Claro, and I'm currently doing my master thesis on the biomolecular structure and function group at I3S. And today I come here to present you some of my work, which is based on the use of small molecules called nanobodies to combat Mercado-Joseph disease. As you probably know, Mercado-Joseph disease is a rare disorder, and it is the most common type of spinocerebellar ataxia in the world. This disease affects the right functioning of the nerve cells in the brain and also in the spinal cord. It is caused by a mutation in a specific gene, and it has an autosomal dominant inheritance, meaning that the children with an affected parent have 50% chance to have the disorder. The main symptom is loss of motor coordination, but there are many others, like, for example, impaired eye movement, slower speed. There is a marked progression of the symptoms over time, and unfortunately, there is still no cure for this disease, only therapeutics to attenuate the symptoms. As I information, this disease is caused by a mutation in one gene, which affects the structure and function of a protein called ATAXIN-3. This mutated protein starts to clump together and form toxic aggregates in the brain. These clumps will affect the neuronal function, leading to brain neurodegeneration. Well, one of the many strategies that are currently being developed to avoid the formation of these toxic aggregates is by silencing the pathogenic ATAXIN-3 so it cannot become malignant for the patient. But the strategy that we are focused at the moment is to avoid this particular step of aggregation. And for this, we are using therapeutic molecules. And the ones that we are using have the name of nanobodies. But what are nanobodies? They are small synthetic antibody-like molecules, and basically they have the function of targeting and binding to evil compounds and degrading them from the body. They are promising because in addition of being relatively cheap, they are very stable molecules that easily enter in the tissues. Our goal is to use these nanobodies to bind to taxin-3 in order to avoid their clumping. For this, we are using an animal model known as fruit fly. We already have flies that in the lab that display Machado-Joseph disease and simultaneously have nanobodies in their nervous system. But why use fly as a test model? Well, they have a very simple nervous system, making them ideal for the study of brain-related diseases. In addition, they are very easy to handle and allow us to analyze their phenotype, motor capacity, and lifespan. But how do we do this analysis? Basically, we can observe the eye of the fly. Flies that we have in the lab without the disease have a well-organized eye structure, while Machado-Joseph disease flies have small and more fragile eyes. We can also evaluate how they behave at a motor level, if they are more or less able to climb the test tubes according to the nanobodies that we are using. Finally, we can analyze the survival of the flies when subjected to different therapies. In the end, we already identified some nanobodies that provide improvements in the eye structure, in the motor coordination, and that extend the longevity of the Machado-Joseph disease fly model. To summarize, we intend to evaluate if nanobodies prevent the formation of protein toxic clumps through the use of a fly. Then we want to evaluate if the nanobodies can really cross the blood-brain barrier and enter in the human neuronal cells. And finally, if necessary, genetically improve nanobodies so they could have a greater efficiency in their action against the disease. With this end up my presentation, I would like to thank all the current team and all the people who previously worked on this study and also all the fundings. I'm now available to answer any question or later. Thank you very much.
Thanks very much, Anna. Everyone hold on to your questions and we'll do them at the end. So next we have Enzo Neo, and he's joining us from University Hospital Essen, and he's going to talk about cerebellar ataxia and fear extinction. You can see he's there, so you can share your screen, I think.
Yeah, almost.
Great.
So hi, I'm Enzo, and I'd like to talk to you about fear extinction and cerebellar ataxia. So an idea I really like by Dr. Schmamann is that the cerebellum does not create, but refines, so that learning is possible without the cerebellum, but the improvement of learning or the refinement of learning is much more difficult without a cerebellum. An example of this is a patient without a cerebellum who was, here on the left, who was able to learn how to drive, but then when faced with a very stressful driving situation, still crashed his car because the inputs were basically too much. He was overwhelmed with the situation. So kind of showing that he's able to learn how to drive, a pretty complex motor learning, but is not able to have very refined learning. And so in the same way that the cerebellum is thought to be involved in movement and motor learning, it's also thought to be involved in emotional learning, or maybe the refinement of emotional learning. And so my lab studies the refinement of emotional learning, and then specifically how the cerebellum is involved in emotional learning of fear extinction, where fear extinction is the learning process of how we become less afraid. And we study fear extinction with Pavlovian fear conditioning. And I'll explain these two terms now, where what we do for fear conditioning in humans is very simple. We show a neutral stimulus, such as a square in our case, and then apply an electric shock that is unpleasant but not painful to the participants. And so when people encounter this scenario repeatedly, they learn to associate the square with the electric shock, and of course will not be happy with it, have increased sweating, increased heart rate. And then as you do this repeatedly, the square will become will have a fear association attached to it. So only showing the square will be enough to increase sweating and increase heart rate, and this is called a conditioned reaction. Then if you keep showing the square over time, the participant will learn and not give the electrical stimulation. Over time, the participant will learn that it's no longer associated with the electric shock, and the conditioned reaction will diminish. And this learning is called extinction learning, or fear extinction. And this is basically what we're looking at in our lab. And so we do these measurements in an MRI scanner, where we measure all kinds of physiological parameters, including heart rate, including sweating, but also measure brain activity with functional MRI. And so we have done this study already in young and healthy participants, but we'll now also do it in patients with cerebellar degeneration, namely spinocerebellar ataxia type 6. You can see SCA6 on the right here, which is progressive degeneration of the cerebellar cortex to accumulation of proteins in Purkinje cells. And what we would expect of these patients is that they will be able to successfully do this extinction learning, basically get to the same end result, but will have a different way of getting there, and maybe have compensate for the lack of cerebellar function in different ways by different brain areas. And then our overall goal is to improve the understanding of the role of the cerebellum in emotional learning, and specifically in fear extinction. And understanding fear extinction better could improve maybe exposure therapy, because exposure therapy, you might know, is essential for the treatment of post-traumatic stress disorder. And fear extinction is thought to be the underlying mechanism of exposure therapy. And so I'd like to highlight lastly that this patient population provides a valuable insight into the role of the cerebellum in fear extinction, and really a unique opportunity to look at the cerebellum and how it's involved in emotional learning. So I'd like to thank you for your questions or for your attention. And if any questions are there, I'd be happy to answer them. Thank you.
Thank you very much, Enzo. So finally, our last flash speaker is Celeste Suard, coming from now the National ATAXIA Foundation, but before that she was a researcher. So this presentation is on exploring DNA damage and repair in SCAR1.
Can you hear me okay?
Great, yeah, go ahead, thanks.
Wonderful. So good morning from Canada. Hi, my name is Celeste, and today I'm going to be chatting with you about some of the research I did in my PhD focusing on DNA damage repair and spinocerebellar ataxia type 1. Before we jump into this, I have a few disclosures. This work was done when I was a PhD student at McMaster University in Canada. Things were simpler then, and I didn't have any financial or commercial conflicts of interest. Now I'm employed by the National ATAXIA Foundation, which receives funding from multiple sources, including pharmaceutical companies, government grants, charitable donations. And with that, let's jump into the science. So why research DNA damage repair? DNA repair is how the cells in our bodies fix the damage that happens to our DNA. This is very important since DNA contains all the instructions that are needed to build our bodies. If DNA is damaged and not fixed, this can lead to problems. DNA repair is Faulty or incorrect DNA repair is most famously connected to causing cancer, but in the past 10 years, incorrect DNA repair has also been connected to different kinds of neurodegenerative diseases like Parkinson's, ALS, Huntington's disease, and ataxia. In fact, there was a huge breakthrough in 2016 linking faulty DNA repair to polyglutamine expansion ataxias like SCA1. This group of researchers, most of them from Europe, found that ataxia patients who also just happened to have mutations in DNA repair proteins would get symptoms either earlier or later than other people with the same kind of ataxia. But this led to more questions than answers. The researchers documented that this pattern existed, but not why it was happening. Since then, numerous ataxia researchers have been exploring the connections between DNA repair and ataxia in many different ways. My small part in that has been investigating whether ataxin-1, the protein affected in SCA1, is involved in DNA damage repair. And there are a bunch of different techniques we use to study DNA damage and DNA repair. Here are two examples of methods that I used when working with skin cells donated by patients. First, we can use laser beams. We can use lasers to cause DNA damage in only a specific area of the cell. We can then measure what proteins travel to the damaged area to fix the DNA and how fast they get there. Here's an example video of ataxin-1 in green moving into the damaged area indicated by the white box. We can also use chemicals to study DNA damage. Treating cells with different chemicals causes different kinds of DNA damage to the entire cell nucleus. And that's the most important part. Different kinds of chemicals cause different kinds of DNA damage. So we can use different chemicals to test how well SCA1 cells can fix different kinds of damage. Here's an example image of what this kind of experiment looks like. In the control image, the cell nuclei are faint, but in the cells treated with KBRO3, a chemical that causes oxidative damage, the nuclei are lit up brightly. So using these techniques, I discovered three main things during my PhD studies. First, that ataxin-1 travels to areas with DNA damage. No one had measured that before. Second, that the mutated ataxin-1 that happens in SCA1 travels to damage much more slowly than healthy protein. And when it gets there, the mutated protein doesn't work as well as the healthy protein. Third, SCA1 cells are able to repair most types of DNA damage really well, but they can't fix oxidative DNA damage efficiently. This suggests that whatever the mutated ataxin-1 is doing at the area of damage, it's causing problems with oxidative repair pathways specifically. But this work is only the beginning. There's still a lot more questions to answer. But if we better understand ataxin-1's role in DNA damage, we could try to fix the errors with DNA repair as a potential treatment. It's very preliminary work, but we did some experiments with fruit flies where we completely blocked ataxin-1's movement to DNA damage whatsoever, and that made the SCA1 flies much healthier. A more immediate implication of this work, though, is for SCA1 patients who are on medications for other conditions. Some medications have the side effect of causing slightly more DNA damage than normal, but for most folks, this isn't a problem since our DNA repair systems can fix it. But medical doctors may want to think more about the kinds of prescriptions they give SCA1 patients and avoid medications that increase oxidative damage. Again, though, more work is needed to better understand these results. And that's all the time I have to chat with you today, folks. Thank you to my PhD supervisor, Dr. Ray Truant, and the whole Truant Lab group for their support during this work, the funding agencies who made this work possible, and to the National ATAXIA Foundation, where I now currently work. Also, thank you to the organizers for the opportunity to present this talk, and to all of you for listening. I'd be happy to answer any questions during the question period. Thank you so much.
Thank you, Celeste. I think it's about 5 a.m. there, so thanks very much for getting up to join us. We appreciate it. And to all the speakers for the brilliant talks. So if anyone has any questions, I think we have a few minutes to do some questions. I can start. This is a question for Anna. Could you talk a little bit about whether nanobodies could work for other ataxias?
I'm not really into the other ataxias. I just work with ataxin-3, but I think it could work also because it could bind also to the other types of ataxia. But I don't want to talk more about that because I'm not studying the other types of ataxia.
That's fine, thank you. Any other questions in the room or on the chat? I have a question for Enzo. Was there a particular reason why patients with SCAR6 were chosen rather than any other ataxia?
I think mostly because we have a decent sample size already for SCA6. And it's also a kind of good pure cerebellar degeneration. So we really don't want any other degenerations for our study.
Thank you.
So welcome to this session, which is to give some patient insight into the areas of research. What do patients want from research? Because it isn't necessarily what they're given. So we want to find out what patients want themselves. So we're going to have to do, I don't know if that mic is working, so we might, no? Okay,
No.
So we'll have to take it in turns and pass the mic down the line. It works? Oh, switch it on. Always a good idea, switch it on. Yes, great. Okay, so I will start here. Please tell me your name and your relationship to ataxia.
I'm John from Denmark. I'm married with a SCAR3 patient who have had it for, she's very ill now. I have two daughters. The one of them have SCAR3 as well, without any signs of illness.
Same question.
Hello to all. My name is Mariana Kotzamanidou. I'm from Greece, especially my birthplace is Pieria. I'm happy to be here. First of all, I want to thank President of Hellenic Ataxia Association, Mr. Karadzias, and EuroAtaxia for this nice session. I'm a physiotherapist and I'm working every day in the water with patients with ataxia from all of the ages.
Ah, now I was expecting you to be a patient.
No, I'm not a patient. I'm the therapist.
I thought we were going to have two Greek patients. Are they expecting to come up to the platform? Are you going to come? Mariana, we will see you in a minute.
Hello.
Your name? Hello.
Hello, I'm Theodosis. I'm a late onset Friedreich ataxia patient. And I'm a father of two kids, one small little boy and a 7-year-old daughter. And we are here to all contribute to this very nice conference.
Excellent.
Hi, I'm Shayna. I'm originally from South Africa, but now living in the UK. I have spinocerebellar ataxia 3 from a long generation of it following down in my family.
Shayna,
Yes.
How long have you had a diagnosis?
So I chose to be tested at the age of 18. In South Africa, you have to go through psychological evaluation before you're given the results. And I had to see a neurologist, a psychologist, what else? There were quite a few that I had to do, and it took about a year for me to be diagnosed.
And at that time, you were or weren't symptomatic?
I had no symptoms. I just wanted to know for my future.
And you had reason to believe that you might have SCAR3?
Oh, no, I do have SCAR3.
No, but before you were tested.
Oh, before I was tested, no. I was just told that there was a 50% chance that I would have the gene.
Because?
Because because of my father. Because he had SCA3, my uncle has SCA3, my grandmother had SCA3. So a very long line of
So
SCA3.
lots of experience before you got tested of
yes,
what
a lot of
do.
anxiety around future planning for your life and seeing what happens when you haven't got a plan in place, even though you know you could get sick. And so I wanted to prevent that. I also wanted to know to have a partner, to get married, so that I informed my partner right from the beginning that I had SCA3 and this is what he was in store for. And surprisingly, he stuck around. And also for children. It wasn't something that I wanted to pass on, and I was blessed enough and fortunate enough to be able to do IVF and PGD, and I have a daughter who does not have SCA3, and I'm really proud of the fact that it stops here with me. Yeah.
How long have you had a diagnosis?
So my diagnosis was back in 2020, so 2 years ago. It was quite a surprise because a few months before that, my second child came to this planet. It's devastating when you hear about this news. You are thinking, okay, what's next? What I'm going to do? Nowadays, I'm thinking that I'm from the fortunate that I have been a late onset. So I had the chance to experience life, to have a family, and I think there is also hope looking forward with treatments and with, let's say, not a cure, which I think it's a bit far, but I think with, let's say, treatment management and all this kind of stuff, we have good chances to have a good life ahead of us.
How long has your wife had a diagnosis?
She have had it for 20 years, and her dad didn't have SCAR3. They said he had multiple sclerosis, and that's not inheritable. So when we were planning to have kids, we didn't get tested. So that's the fortune you have today that we didn't have. Oh, that's the fortune you have today that we didn't have. Yeah.
So for you now, what are the biggest challenges of your wife's ataxia?
My wife is very hard degenerated. She can't do anything herself. And for the last half year, she has also been mentally gone. Sometimes she disappears in a couple of days, then she comes back, and we have a lovely hour, and she'll disappear again for a few days, and yeah. And when she's back, the largest and biggest impact is the way of speech, the way of communication, the lack of it. That's the biggest issue.
And for you, what are the biggest challenges for you about having had a diagnosis of FA?
All the forward-looking statements when you are diagnosed that back then there is no cure. It was so devastating. Today there is a, as I said, let's say, drug that can stop the progression. The challenge for this today is to get access, a fair access, which I think should be a case to discuss also with the researchers. I mean, what's the point to find a drug if we cannot give it to people, right? So it's something that should be questioned. And of course, I think the biggest challenge for me is, okay, I have a family, I need to take care of the family, and also what's the next steps on these regards.
Shana?
So I'm fortunate enough to not have many symptoms that affect my life in any big way, and I really can't complain. But I'm also quite honored and privileged enough to represent a community of people from ATAXIA UK. And I sent it out, this question to the community, and I asked them, what could we do for them? And fatigue was one of the biggest symptoms that we could be looking into doing. And also fine motor. So we have someone who used to love playing guitar, and because his symptoms have progressed, he cannot play his instruments anymore. And I think it's so important that we do look at ways to keep people doing what they love to do.
So staying with you, Shana, if you were to be advising researchers on SCAR3, given that you've seen other members of your family with SCAR3, even though you haven't got many symptoms at the moment, what do you think the most important symptom to treat at the minute would be?
It's such a difficult one, Sue. But I do feel that speech, like John was saying, because even though when my father was sitting in,
Take your time.
Even when he was sitting in a wheelchair, there were so many years in that wheelchair. So yes, we couldn't fix his walking or his ability, and we still took him places and we still did things. But I would have loved to hear him tell me stories or give me advice, words of encouragement. Yeah, so I think speech is a really, really big one. But also, like I said before, for research to look at ways to keep people doing the things they love, playing instruments, reading, because of nystagmus can be difficult to do, singing, and I think voice banking is also so important because you can do that through that. But definitely new ways to look. And the other thing my father loved to do was eat. And gather his family together and have a big meal. And towards the end, he couldn't do that. He couldn't eat. And I think if we can put people on the moon, we can surely find better ways to keep our family members fed and enjoying the things that they love to do.
For you, Theo, what do you think would be the most important thing to have a solution to?
Friedrich ATAXIA faces a lot of challenges. What I would like today, at least, to put in the table for researchers is that the biggest inventions in the world has happened out of observation, right? So I think somehow we need to have a system, an SOP that I heard previously, to report patient outcomes. So I'm crazy enough and I'm trying A. Some other is crazy enough to try B. What happens? Because everybody is different, right? So now I'm trying to have, let's say, an exercise life and nutrition. Nobody's studying what's happened to me unless I am on a very sterilized environment within a clinical trial, right? Where everything is standardized to be comparable. But I think this kind of data is important. And one more thing. Studies and outcomes is a numbers game, right? So it's a matter of how quickly we study data. We see now the rise of AI. I would like to see on these data teams in hospitals, 1 or 2 persons starting to use in AI to study data faster. Because if we do things faster, we will deliver more treatments. I hope it makes sense.
John, you're at a very different stage of the journey. You've seen it in nearly its entirety. What 3 things would have made the journey better, easier, helped you meet the challenges?
I think it's a difficult question because we have done everything right all the way, I think. One thing could be more resources for the researchers and neurologists. My wife have had excellent physiotherapists, excellent carers, and the one thing that's difficult for this journey is to keep hope all the time and keep them motivated to continue. Do not give up. And that's one of the difficult things as a husband to one who is so difficult affected by the disease. But in other countries, they don't have the same level of service as we have in Denmark. So I think this community needs to help those countries who have difficulties in training sessions and psychologists and neurologists. We have to make an effort for the other countries as well.
Would each of you agree with the results of the survey that Shana did, that actually fatigue is a neglected symptom of ataxia? In the UK, there is a charity that works in arthritis. It's a very wealthy charity. And about 6 years ago, or 7 years ago, it had a good look at itself. It, at that point, was being governed and managed by clinicians, and they went out and did a survey of their patients. And they were astonished at what came back and how little attention they had given to it. And in arthritis, I'm sure that people know that pain is the issue for patients a lot of the time. And Arthritis Research UK had never spent a penny on investigating pain. And it seems to me that we have a very close relationship between researchers and patients. There are a number of researchers here who will have seen patient panels like this before. But I wonder how much money we have invested in research into fatigue, and yet everybody complains of it. So perhaps there is some way that we can get a hold of fatigue and see how we could help people to energize themselves a bit more so that they can keep themselves more mobile and thereby enhance quality of life, even if we do not have treatments and cures for the other symptoms. I want to thank the patient panel for coming up and sharing. I know it's not very easy to do these things publicly, but I'm sure it's really important for researchers to hear from patients, to know what their big issues are, and I would encourage you to have interactions with patients whenever you can, and to take advantage of patients being here to ask them, and so that you can have a first-hand understanding of what their experience of ataxia is. Thank you very much to Theo and to Shana and to John. I'm sorry, Theo, I don't know you very well, but I know that both Shana and John approach their ataxia and their connection with ataxia in an amazingly positive way, which inspires other people. So thank you, all three of you. Thank you.
Thank you.